right? So, just like when you learned, the derivatives in 1801, right? You don't use the definition of a derivative. It's some limiting procedure for every time. You learn some product rules and power rules and sum rules and those kinds of things. So we can do the same kind of thing. Let's do an easy one. Let's do a sum rule. Let's suppose you have an f, a function f of x is g of x plus h of x. Let me drop my vectors, but you can understand that everything here can be a vector, right? The x's can be a vector, and the f's and g's and h's can be vectors, right? And in fact, in an arbitrary vector spaces, we'll see very soon, right? Then, if I want df, that's just going to be just write it as dg plus dh, right? Or equivalently, this is f prime of x dx equals g prime of x dx plus h prime of x dx. So f prime equals g prime plus h prime, right? Just the obvious sum rule. I don't know if you want me to derive this. I mean, again, it just comes from the definition. If I take f of x plus dx minus f of x, addition is linear. It's g of x plus dx minus gx plus h of x dx minus dx.
I don't think anybody in the room doubts it.
Yeah.
You don't have to exactly derive it.
Yeah. So let me do the product rule. Right. This one starts to be a little bit. I should do this on. Well, I'll write it out first. Suppose you have, and I'm just going to write. Do I need to write the f? Sure. I'll write f of x equals g of x times h of x. Right. So these have to be things you can multiply, obviously. Right. So if these could be two numbers, or they could be two matrices, but they're of the right size. They can't be two column vectors, at least not with the ordinary. I'm just doing multiplication here. Maybe I should do element-wise multiplication in a minute, but let me just do multiplication. Okay. And so then df is going to be just dg times h plus g times dh.
And I guess the point is, whenever GH makes sense, whether it's element-wise products or matrix multiply, if it makes sense, then the rule holds.
Yeah. So if you think about what this means in terms of f prime, right? This f prime of x dx is going to equal g prime of x dx times h plus g of x h of x plus g of x times h prime of x dx. And I cannot necessarily write f prime equals g prime h plus h prime g, because I can't commute. Let me. I'm running out of space here. Why can't I do that? Because I can't necessarily move the x to the side here, right? So g prime dx h is not equal to g prime h times dx, right? In general, if these are numbers, obviously this works. But now that these could be some other kind of object, matrices or something like that, this is not going to work in general. Okay, so let's derive this. Just to we already kind of derived it, but let's do it in general. This is derivation, right? So f is in GH. So what is df? Just use our definition. Df is going to be f of x plus dx minus f of x. and f was g times h. This is g of x plus dx times h of x plus dx minus g of x, h of x. And then this is g of x plus dx. We said by the definition of the derivative, that's g of x plus g prime of x, whatever that linear operator is, times dx, times h of x plus dx, and h of x plus dx, same thing, is by the definition of the derivative, that's h of x plus h prime of x minus g of x, h of x. And if we just write out all those terms, and again, these might be matrices or something, I can't change the order, but I'm assuming that if this is a multiplication operator, it could be element-wise, or it could be just matrix multiplication, anything that satisfies a distributive law. I can write this as gx h of x, that's this term times this term. There's also this term times this term, this term times this term, and this term times this term. This term times this term, sorry. So I get plus g prime x dx times, which I could also just write as dg. Right? This is the same thing as dg. This is the same thing as dh. Maybe I should have done that just it's a little shorter to write. This is dg times h plus I have a g times dh plus I have dg times dh, but that term we're going to ignore. This is higher order. This is right. So that's gone. If d is arbitrarily small, that's infinitesimal, and then we still have the minus g of x, h of x term here, and that's it, right? So now so we're done. This is
And this is really nothing but a copy of what you did in, the first month of calculus when you first learned it, except that we are just extending it to, vectors and matrices and making sure that we don't mess the order up.
Yeah.
Otherwise, it's exactly what you did in the early days of calculus. I'm sure you all remember.
Yeah, and let me just do a couple examples. Suppose when we just had f of x equals ax, right? Then df is equal to dA times x plus a times dx. But this is 0 since a is constant. A is independent. It is independent of x. So remember, you always have to keep track of what are the inputs, right? So here, df, f is a function whose input in this case is x, right? So df really means f of x plus dx. F of x plus dx minus f of x. So since a doesn't change with x, that's 0. So then I'm done. Right? This is I get the same term I got before.
Let me ask the class, and not you, Stephen. What 0 is this? Right? I think that might be useful to think about. What can someone tell me exactly which 0?
Shape of 0, yeah.
Shape of 0. Sorry? Is it m-dimensional column vector? No, I don't think so.
A is m cross n.
Yeah. So what is dA?
That's square matrix. M cross n matrix.
Yeah, it's an m by n matrix of zeros. So that innocent red 0 that Stephen drew is really the m by n 0 matrix. Right? In fact, you could have written dA equals 0 dx might have pointed that out. But it's so easy to quickly look at that 0 and lose sight of the fact that that's an m by n 0 matrix, which if you multiply by any dx, that's that's n little perturbations, you get m zeros coming back out.
Yeah. So let me do another one, the one that I did before. So I did x transpose ax, I believe, right? So now if I do df, I get dx transpose. This confuses people, by the way, a little bit. So if I do, why does, well, it actually, why does dx transpose equal dx transpose? Because it's just dx, dx transpose is really x plus dx transpose minus x transpose, but that's equal to x transpose plus dx transpose minus x transpose, so that's dx transpose, right?
I would have thought of it that way, but of course it's right.
Yeah.
To me, it's just like you just take something as a column and you make it a row and you perturb either way. It's sort of the same thing. But
Yeah.
but formally, you're quite right, Stephen. To do
Yeah. So
but I like
and so in homework, I want you to think of this in terms of linearity, right? The transpose is well, I mean, I'm kind of giving away though, but transpose is an example of a linear operation on a vector. And it's one that's kind of annoying to write down as a matrix. But because it's not really multiplying x by a matrix unless you reinterpret the output as a vector and the input as a vector in some way. So anyway, so this is, let me just go back to the product rule. I guess I only showed you the product rule for 2 terms, but it's the same thing for 3 terms. So there's df.
You could talk about the product rule for 3 terms, or you could think of this as 2 terms and use the result that's on the top of your screen.
Yeah, I could exactly. I could just use
it now, right?
Yeah, but let me just do it for 3 terms. But yeah, I could use 2 terms, and then you write it as, let's do it with 2 terms. So this the x transpose times d ax, right? And that's equal to dx transpose ax.
So in effect, you're putting a parenthesis, like you're around it's x transpose times left paren ax right paren is your f now, right? You see what I'm saying?
Yes.
Your f effect itself is thought of as x well, even high. Yeah, that's what I'm thinking.
You're thinking of that, yes. So and of course I can put parentheses anywhere I want in these kinds of things.
Of course you could, but that's what you're focusing on this way, right?
Yeah. So and dax is product rule again, but I just did that, so it's adx, right? And then we use the same trick before to this term here is a scalar, so I can just transpose it and get the dx on the right, and so that's equal to x transpose a plus a transpose dx, and then this was our f primed of x, which is the same thing as the gradient of f transposed, right? So which therefore means that the gradient of f is equal to the transpose of that, which is a plus a transpose x, right? So that's the product rule, pretty straightforward, right? We could do more complicated things. So we could do, for example, but let me hold off on that for a second. Let's do the chain rule. So suppose we have an f of x equals g of h of x, right? So h of x is a function, takes a vector in, gives you maybe, or some x in gives you some vector out in some vector space, maybe numbers, maybe column vectors, maybe matrices pretty soon. And g takes whatever the output space of h is and gives you some other vector as output, right? So for example, x could be a column vector, and then h of x takes a column vector, produces a matrix, and then g of x takes a matrix and gives you a scalar, for example, like a determinant. Okay, so they could be all different shapes, right? And one of the things we talk about in linear algebra is it's always good to keep track of the shapes of things. When everything's not a number anymore, so you need to keep your shapes sort of lined up. Okay, so then what's the chain rule going to be? It's going to be I'll just write it down first and we'll just see why. F prime of x, right? That acts is a linear operator acting on a dx, right? And that's our df. Let's maybe write that down. df equals that. Okay. And what do you do? It's going to be work just like the chain rule for numbers. It's going to be g primed of h of x. That's a linear operator. And that's going to act on h primed of x. And that's a linear operator. It's going to act on dx. I guess we're not putting vector signs in there. And as very often I'll drop the f prime of x equals g prime of h of x, h prime of x. But when I write a product like this really means the composition. It means it's a product of two linear operators of g prime and h prime. It means you do h prime first and then g prime. And this is very much not equal to h prime times g prime. Right? You can't think of these, for example, as matrices, right? You can't change the order.
Steven, can I throw in something that's a foreshadowing of something that might come later, but just to set a stage? I want to ask the class from ordinary calculus, just an application of the same chain rule. Like, let's say you were taking just the derivative. You all can do this. Derivative of sine of x squared. I want to ask how many of you will first do the cosine. So it'll be cosine of x squared, and then in your mind we'll do the 2x. And as opposed to how many of you will do the 2x on the inside first and then do the cosine? So how many of you are cosine first people? I think that was everybody. Does anybody do the x squared first, going in to out? There are two people in the back who do it. But you see, of course you could do it either way. And just to say some words now that will come up later. The first way is what eventually becomes forward mode automatic differentiation, if you've ever heard that term. And the second way is reverse mode automatic differentiation. Of course, for scalars, it's all pretty simple, but when we get into this matrix calculus stuff, it gets to be sort of the whole big thing of, machine learning and lots of other things that, technologies that underlie so much these days, right? So, but it really, in its simplest form, it all boils down to, as Stephen writes, you have the choice, in effect, of doing the h prime first or the g prime h first, right? If you're a computer, you'll have to do it sequentially, right? So one of the things will come first. I guess it doesn't have to be sequential.
Yeah, and I'll show an example of that in a second. So I think it becomes more clear once you have three things.
Yeah. Okay. All right.
So
I just want to set that thought up.
Yep, absolutely. So it's really going to matter left to right. When these are not scalars anymore, the left to right versus right to left is going to start to matter a lot.
And also the order.
Yeah.
Right.
So yeah, I don't know if people want me to derive this again. We can just plug in the definitions and do f of x. Take this plus dx, minus g of h of x plus dx minus g of x. It's g of h of x. Sorry, and then
the derivation.
Stand out everything and just drop the dx's.
What is the derivation? Who wants to go straight to the application? Derivation? One
derivation.
Person. How many wants to see the application? Like 5 or 6 people. So
okay.
Right.
So let me do an example of just to suppose that to start with that so the x, our inputs, live in Rn. Okay, so we have n component vectors as inputs. And then suppose that h of x, our first function, our inner function, lives in our P. They're P, so it sends vectors to vectors. What happened? Okay, there it is. And suppose our outer thing, our G of H, lives in our M. So if we do f of our f of x, right, which is now going to be is remember it's g of h of x, right? What it does is it sends things in Rn through to Rp via h, and then sends them via G to Rm. Okay, so it sends vectors to vectors to vectors, maybe all the same size, maybe not. Okay, and then what is our chain rule? Right, is that f prime, that's blue, f prime, okay, of x. And so now we know this is a Jacobian matrix. This takes n inputs, m outputs. This is an m by n Jacobian, right? This is equal to g prime times h primed. So this is going to be g prime of h of x. And G takes P inputs and as M outputs. So this one is an M by P Jacobian of G. And I think I might need a little bit more space. I love that I can do that. On the blackboard, I always write and to get to the edge of the blackboard, and then my writing gets tinier and tinier. And then, sorry, not equals, times h primed.
I've seen people move over to the walls when the blackboard space ran out.
Of x. And h prime of x takes n input, h has n inputs and p outputs. Right? So it's a p by n matrix. When you linearize it, it's a p by n, right? These h and g are not linear functions in general, but when their derivatives are the linearization, there are linear operators, they're just matrices in this case. And you can see that these match up, right? This not only is this not equal to h prime times g primed, right? But that wouldn't even make sense, right? This is right. If you multiply a p by n times an m by p, that doesn't even work, right? So you really can't change the order of these things. So this is nonsense, I guess, if n is not equal to m. Right? Even if n equals m, that product means something, but it doesn't actually, it's not equal to the derivative of f anymore. Derivative, that would be the derivative of g of h of x if you swap the order. Right? So for just functions that have vectors in, vectors out, the chain rule is just the ordinary product, the matrix product of Jacobian matrices of each of the terms in the order. So you always have to go keep them in the same order, otherwise it's not going to make sense. Where the outputs are here, then the outputs of h are there, and then the inputs are finally there. So not only does the order matter, but the associativity matters practically. right? And associativity is going to matter where you put parentheses. So here, I'm just multiplying two things. There's only one product. There's only one choice. But suppose we have three functions. Right? So now suppose we have f of x equals, let's see, should I still try it in blue? Let's see, f of x, right, equals, let's see, I'm running out of letters. GH, what letter should I use? A. Well, no, let's use ABC. Let's use ABC. A of B of C of x. Right? And suppose that suppose these all have different number of components. These have, suppose this has, F has M components. Suppose that X has N components. And these have, let's see, C has P components. P and B has Q components. And then A, let me color code it. So A is the output, so that it has to be the same as F, right? So then what is F primed? So that's a function of x, right? It's just a product of the three Jacobians. So it's A primed of x. You might put in my x's in red. Let me just not put x's. You know that the x's are there. It's A prime times B primed times C primed, right? And A is M by Q. Where my M's are in blue. By Q. B primed is Q by P because it takes P inputs and has Q outputs. And C is P by N because it has P inputs and Q outputs. And so this, I can now, so I can't change the order. This is matrix multiplication that's not commutative, but it is associative. I can always put parentheses. I can always multiply from left to right or right to left. So this is doing it left to right and right to left. And these are going to have, it seems like it's, who cares, right? You just do it in whatever's order is convenient. It turns out it's incredibly important. This one from left to right is called reverse mode. And this is called forward mode differentiation for an automatic differentiation.
You see the reason for the names that, if you know, at first glance it looks like the names are backwards. It looks like reverse mode's going left to right, which is, you know, forward in English and many languages, and forward is going the other way. But obviously forward mode refers to the first function is C, then B, then A, and it's respecting that same order. So it's forward, right? The reverse mode is going ABC, which is sort of the reverse order in which the functions are applied.
Right. So forward mode is going from inside out, is like from inputs to outputs, from starting with the input C and then going outwards. And reverse mode is going from outputs to inputs. So why does this matter? I claim that this matters. And the reason it matters is that the multiply matrices, how costly it is depends on the shape a lot. And so let's think about the cost of matrix multiplication. So if I do if I do, what am I doing here? Like M by Q by P times P, or M by Q times Q times P, right? So if I multiply an M by Q times Q by P matrices, so the result of this is, of course, an M by P matrix. So how do you do it? So for each entry of the output, you've probably learned row times column, right? So you do it for each component of the output, you do a dot product. So this is MP dot products of length Q. Is that clear? Right. So for each entry, if I imagine this as this is a matrix, for each entry here, I do a row times a column. And the rows have Q entries, and the columns here have Q entries. So it's a dot product of length Q, and there are M times P outputs. Right. And so the cost, how much does a dot product cost? Well, to take two dot products of length Q, a dot product of length Q, right, in blue. So a dot product of length Q costs Q multiplications, right? Because you have to multiply Q things together. And Q minus 1 additions, of scalars. So basically, it's proportional to Q scalar operations, which is what the CPU is doing. So the whole thing is proportional to M, P, Q scalar operations. Right? So that's a review. So if I do, for example, if I do M by M times M by M, two matrices, this is proportional to M cubed. So we would say, in computer science, you would say this is theta MPQ, right? That notation for proportional to, that big O notation, right? But I'll just say proportional to M cubed, right? If I do M times M by 1, so if I do a matrix times vector times a column vector, that's only proportional to M squared. I only do M dot products. Or if I do 1 by M times M by M, so if I do a row vector times that, that's also proportional to M squared. So why does this matter? Does the order of the chain rule matter? So suppose you have lots of inputs and only one output. So let's do
Machine learning.
example, like in machine learning. So we have many inputs, lots of inputs. Actually, my inputs are red, right? So lots of inputs. N is large, right? And only one output. So M equals 1. So this would be the case, for example, in most of optimization, right? So in large scale optimization, or for example, such as machine learning. So in that case, the output is called the loss function or the objective function. So, and these are the parameters. right? The optimization parameters. So in machine learning, for the neural network, you have a big neural network, it has 1 billion parameters in it. And you're trying to optimize those parameters to make one number better, right? Let's have something called a loss, something measure of accuracy of whatever the neural network is trying to predict, for example. You're trying to make that measure of accuracy better. So you have one output and 1 billion inputs, okay? And let's also suppose, let's suppose we have lots of intermediate values, what was I calling those? Q and P. Right? Suppose those maybe are comparable to N, right? So this also happens in a neural network. You have 1 zillion inputs, right? And they go through a bunch of stages of the neural network that have lots and lots of values at each stage. And then finally, at the very end, that all those outputs, you have a zillion outputs, like maybe it's trying to predict an image. And then that goes through one function that's like, how accurate is that image? You know, how well does it match if you're trying to generate images of dogs or something like that? Or how good is it, right? Or this happens in engineering optimization, right? Which is so not really data driven, but suppose you're trying to design an airplane wing that is as strong as possible. Then you have 1 zillion inputs, which are describing the distribution of all the material, you know, over the whole shape of the airplane wing. But you only have one output at the end of the day, which is your one number, which is like some measure of this, how strong it is, how much weight can it hold, or something like that, right? And you take those zillion inputs, get 1 zillion numbers, which are all the stresses everywhere on the airplane wing, and then pass it to another function that takes all those stresses and works out the strength of the wing. And that's what you're trying to maximize, right? So then think about what the shape of the chain rule is, right? So our F prime, right? So this is one output by n inputs. So really, this is a gradient, right? This is what you're going to typically want in optimization machine learning. We'll talk about this more later. That you want the gradient gives you basically the direction, the uphill direction, or the downhill direction is minus gradient. It tells you in what direction do you perturb the parameters to make your system better. Like in what direction do you change all the parameters in the neural network to make it more accurate, to make the loss less? Or in what direction do you perturb all the parameters describing the shape of your airplane wing to make it stronger, right? So that you really care about getting this gradient, these n numbers. Okay, but what is that in terms of the chain rule? We said it's G prime times it's A prime times B prime times C prime, right? So it's A prime times B prime times C prime. And we said A is M by Q, M is 1. So 1 by Q. Let's just suppose for simplicity that these are just equal to n. So this is 1 by n. B is n by n. C is n by n. C prime is n by n, right? Because you see, C takes n inputs, your x's, gives you n intermediate outputs, P, and then B takes those n things and gives you another n, so it's Jacobian is another n by n, then you multiply by A. And notice it really matters where you put the parentheses, because if you put the parentheses here, think what you're doing, versus if you put the parentheses in the other place, A primed, B primed, C primed. If you do forward versus reverse mode, right? So if you put the parentheses here, this is our reverse mode. AD. You're doing this product here is a row vector times a matrix. Vector times matrix is cheap. That's M proportional to n operations. And then what's the output of this? It's the whole thing, the product of vector times matrix, row vector times matrix, is another row vector. And so then you multiply this row vector times a matrix. So you have the whole thing costs order n cost.
Vector times matrix, Stephen?
Sorry, order n squared, sorry. Yes, it's proportional to n squared, right? Because it's vector times matrix, right? Whereas if you do forward mode, if you multiply right to left, what's the cost? Well, you're doing B times C first. This is matrix times matrix. That's much harder. Matrix times matrix is n cubed operations, and then you multiply by a vector, which is n squared. So the whole thing ends up being n cubed. So you really, really want to do it in this order.
This was probably a good time to take a few minute break. We're a little late on.
Yep, and let me just say, so that we're going to take a break in a second, but so this order it's also called, this is reverse mode. It has a lot of names. It's also called back propagation, which, and it's also called an adjoint, differentiation. So this is, and it's the key to optimizing functions over zillions of parameters. It means that I can compute all the derivatives with respect to all the parameters in a quite a reasonable cost. And basically it ends up being in cost proportional to the cost of just evaluating f. Whereas if I did in the opposite direction, if I have a billion parameters, it becomes a billion times more expensive.
And I do like to stress that most students, and when I did the poll earlier in this classroom, it showed itself. Most students, even for scalar calculus, do the outputs towards the inputs, right? Working their way from output. When I asked you about sine of
the forward mode, yeah,
or sine of x squared or whatever I asked, you're all doing, without even thinking about it. It's all second nature. You're going from outputs to inputs, and so this reverse mode, which is often more efficient for many real applications today, is also exactly what you're doing instinctively without even thinking about it.
Yes, well, depends. When it's more complicated functions, so sometimes reverse mode is like, usually when you're doing more complicated things, I would say the forward mode is often the more obvious.
Well, that's right. I wasn't going to say that today.
Yeah, but and we'll talk about that. And we'll talk about more about how these things are evaluated. How many of you have heard of backpropagation, by the way?
Everybody but one.
Everybody but one. But how many people knew that it was just multiplying Jacobians left to right instead of right to left?
Only 3, including one who never heard of the term backpropagation.
Okay. So yeah, and we'll show more examples of this. It's one of those things that, like, once you see it explained, it's like obvious and trivial. It's just left to right versus right to left, after all. I think that until you see it explained, like so for example, if you're computing the drag on the strength of an airplane wing as a function of 10 billion parameters describing the shape of the wing, it's a really huge mechanical simulation, like a solid mechanics simulation, to calculate the strength of that wing for given its shape. And it's really non-obvious that you can get the derivative of that strength with respect to all billion parameters with basically one additional mechanics solve. And it turns out that's another instance of this same thing. But once you see it explained, and we'll see that kind of example more explicitly later on, I think it becomes much more straightforward. But it's really surprisingly non-obvious when it gets to complicated functions that you can do this.
Okay. But I think maybe this is just a great time to just take a 5-minute break.
Yeah.
So I've got 12:23 on the clock behind in the back of this room. So how about we reconvene at 12:28?